I am Julian Erskine, and my co-authors Stéphane, Caro, Zhen, and Chriette are also with us on this video, presenting the design and control of a variable aerial cable-towed system, a paper that we wrote for the IEEE Robotics and Automations letter, and that also got accepted for presentation at ICRA 2020. So in this presentation, we're going to introduce the concept of this novel robot. We're going to discuss the modeling and controls and performance analysis and design of this robot and conclusions about the future of this type of robot. So the aerial cable-towed system is composed of several unmanned aerial vehicles, normally quadrotors connected to a payload using cables. On the left, we see an aerial cable-towed system with 3 quadrotors and a point mass payload that we developed in our lab. And on the right, there's a different architecture of the ACTS called the fly crane, which was developed at the LAS laboratory in Toulouse using a rigid platform and 2 cables per quadrotor for full pose control and 6 degrees of freedom. The advantages of the ACTS are that you're able to share a payload between multiple quadrotors, allowing a larger payload capacity. It's also modular. You can continue to add quadrotors, allowing for greater flexibility in fleet management. And it's able to achieve full pose control of the payload, which isn't available to individual quadrotors. The problem is that they are quite cumbersome as they occupy a large volume, as well as coordinating motion. There's problems coordinating motion between the quadrotors, and internal forces in the cables make them less energy efficient. This paper mainly works to resolve the problem in the first point, that they're very cumbersome. However, it can also have benefits to mitigating other drawbacks. So within this system, the variable aerial cable-towed system, we've developed it for agile operations in cluttered environments. That is, when the environment imposes constraints on the geometry of the robots. Longer cables can make a robot that's more robust to quadrotor pose errors, thus stabilizing better the payload. It also allows more vertical cables while maintaining distance between the quadrotors, which minimizes the internal forces in the cables and creates a more energy efficient system. Shorter cables, on the other hand, are often needed to meet environmental constraints, and shorter cables also make for a more agile system that can redirect quicker. Also, by adding actuated cables, we may be able to achieve better payload control and reshape the wrench space of certain architectures of the ACTS, such as fly cranes.
We propose some assumptions for modeling. For example, cables are massless and inelastic. Cable tensions should be strictly positive. In order to formulate a general model, we assume that the system is composed of N quadrotors, M cables, and winches, and a payload. There should be 1 or 2 winches mounted on each quadrotor. Here is a highlighted point. We do not assume that cables pass through the quadrotor central mass, unlike existing models. The geometric model is derived from the forward and backward derivation of the coincident point I, and the green point I is a coincident point between the cable and winch, as shown on the right. The kinematic model describes the relationship between the movement of quadrotors and the change of payload pose, cable direction, and cable length. The payload dynamic model includes an external wrench from the environment, an inertial wrench from gravity, and a wrench from cable tension. The quadrotor dynamic model includes thrust wrench from motor, inertial wrench, and wrench from cable tension. Further, the inverse dynamic model can be derived and used in the control law. The overview of a centralized feedback linearization control diagram is shown on the right. The desired thrust F represents the reference thrust generation of quadrotors for shearing burden. Then the quadrotors can be stabilized by attitude controller. The aim of the attitude controller is to provide a desired thrust force and stabilize the orientation of the quadrotor. The velocity control loop represents the control loop of winches. Using the controller, cable lengths can be actuated and controlled by servo motors. Range analysis is obtained by 3 spaces in previous work. Because the winch prevents cables from passing through the quadrotor center of mass, a propeller space should be proposed. It represents the thrust force that each propeller can generate. Then the thrust space is obtained by space mapping from propeller space. The thrust force space of ACTS is constant while it's variable for VACTS. After mapping through tension space and the range space, we can get an available range set. The shortest distance from the task space to the available range set is defined as a capacity margin, which is the black line in this figure. For example, the figure on the left shows the capacity margin for different task range. Based on range analysis, we can optimize the prototype design. For the same system configuration, the VACTS needs extra energy to compensate the moment. Therefore, the range should be mounted to the quadrotor as close to its centroid as possible.
So from the analysis, we can find the only primary kinematic advantage of the VACTS is an improved manipulability. However, its benefit is more on an operational level. It does present drawbacks, such as a lesser ability to withstand external wrenches due to the extra weight on the quadrotor due to the winches, and also the geometric inefficiencies of the design when the cable doesn't pass exactly through the center of mass. Or these drawbacks can be mitigated to close to original performance through a design procedure. So here we present a prototype that we developed in the lab. On the left, you see it in flight with 3 quadrotors manipulating a payload of 700 grams. On the right, we see the winch that was mounted on the bottom of each quadrotor. We're using a 2-centimeter drum and passing through a guide bar to maintain a constant position with respect to the quadrotor. We used the Lynx Motion Crazy 2 Fly quadrotors with PX4 running with Pixhawks running PX4. Here we see the drones taking off, and then they lift off with the payload. Trying to hover with the payload at a specific point, we then set the winches to a constant length. And then once the system is stabilized at the desired point, we begin to reduce the cable lengths. The initial cable length is 1 meter and 45 centimeters, and we reduce that down to 1 meter. We see that we're able to track on the right the cable lengths quite closely. 2 of the cables tracked within 1 centimeter root mean square error, while the third cable had a deviation of 3 centimeters root mean square error. This is likely due to a faulty servo motor that wasn't well identified. On the left, we see the performance of the payload tracking. We tracked the position of the payload with a root mean square error of around 14 centimeters. So the primary benefits of this system are the operational flexibility with respect to environmental constraints, and also with respect to optimal configurations, whether that be kinetostatic configurations or energy conserving configurations. It also has the potential, although hereto unconfirmed, to improve payload precision by fine-tuned control of cable lengths. The problems are that we limit the peak kinetostatic performance, meaning that it's less capable of interacting with the environment. It's more complex to control, especially when the cable does not pass through the quadrotor center of mass. Furthermore, the larger state dimension may require new studies for motion planning in order to optimize the operational flexibility to improve maneuvering in cluttered environments and to optimize the various features of this new robot. Thank you for tuning in.